Hello everyone, welcome to the video series of buffer overflow exploits. In last two videos, we saw how to debug those applications. So we used SLMail in video 1 and then minishare in video 2. We were able to control EIP register, we were able to control the program execution with the help of EIP and ESP. So in this video, we have another application and that application is Blaze DVD. So we will use this exploit basically, and I have downloaded and installed this application on my Windows XP machine. So we will first do the debugging with the help of Immunity Debugger, and then we'll try to gain the access of the system. So I have this application installed on my machine. So let me launch the application. And if you see in the exploit, this exploit creates a PLF file, and that PLF file has basically the junk characters. Here it is sending 260 A's. So I'm assuming after 260 A's the application gets crashed. So let's test this. So I have a small code on my machine. Let me show you the code. So it's a user bin Python. Then we will create a file. Then we want to put the 700 A's in this file, and then we are closing this connection. We are closing this file. So this Python script will generate a file with the name dvd.plf, and that file will have 700 A's. So let me close this. We have our application running, and then go to Immunity Debugger. So let me launch Immunity. Go to File, Attach, and Blaze. So I have attached a process with the Immunity Debugger. Let me start the Blaze process and go to this DVD, open playlist, and then we should see one PLF file. So let me go back here. Let me execute the script, and now we have one dvd.plf file. dvd.plf we will select here, and we could see application has crashed. And interesting part is we could see EIP has been overwritten by user supplied input, which is 41, 41, 41, 41. That's great. So we could see application is getting crashed. So now next step is, again, from past two videos, we need to generate 700 unique characters. Then we'll try to identify offset. We'll try to send couple of B's if we are able to overwrite EIP. So that's something you have seen already in these last two videos. So let me quickly execute these two steps. User share metasploit, okay, tools exploit, and then create patron create -L, which is 700. And then we will put this into a Python script, and that Python script will generate a new DVD PLF file. Sorry, I have done a copy here. Let me delete this PLF because Immunity Debugger is attached, so we might not be able to delete. So let me click on exit. Okay, so delete it, open dvd.py, and instead of the 700 A's, now we are sending unique 700 characters. Let me close the double quotes. Okay, and then save the file, generate a new PLF. We have now new PLF. Go to all programs, Blaze, and then launch the Blaze again. Go to trial, Immunity Debugger, and attach this process, Blaze DVD. Perfect. and then try to crash the application using a new PLF file. Great, we could see application has crashed, and now we could see EIP has been overwritten by a number. So let me quickly see what is the offset of this number. User share, instead of pattern create, we have now pattern offset, and we have to see what is the exact offset here. So 37, 69, 41, 36. So exact match is at offset 260. So first 260 bytes. So right after 260 bytes, so next 4 bytes will overwrite EIP. So that's for sure now. So we will send 260 A's and then 4 B's. And interesting part here in this application is, if you go to ESP, that's the change between this application and last two applications. Go to a stack, we see ESP has been overwritten. Sorry, my phone is ringing. Okay, so ESP has been overwritten by this number. So let me see what that number is and where is the offset for this number. So let me do a offset again for 6A, 41, 33 and 6A. Sorry, it is 6A. So let's see what is the offset here for the ESP. It says, so something, so that's my mistake basically, not 6.1, it is 6A. 6A, 41, 33, 6A. Okay. Now let's see what is the offset for this. So offset is 280. If you remember in last two videos, after the 4 bytes for first junk characters, then 4 bytes for EIP, and then from next 4 bytes we were able to see ESP was pointing to. But here we see a gap. So EIP has been overwritten at 260 offset and ESP will start from 280. So we need to add some more junk characters in it. So ideally 16 junk characters. So 260 A's, 4 B's, and then let's say 16 knobs or C, and then after that we should be able to see some data in the ESP. So let me show you how we can test this. Let me quickly exit this from Immunity Debugger. Now go to Python folder, delete this PLF file and click on edit. I don't need this anymore. Wait. Let me maximize this and delete this entire row. Okay, so we need to send A. So we will send 260 A's. Then we will send B, which is 4. Then we will see, let's say C, and that should be 16. And now we will send D, which is 700 minus 260 minus 4 minus 16. So we will send 260 A's, 4 B's, 16 C's, and then rest of the D in this Python script. Click on save, launch the application again. Trial, close this and start the Immunity Debugger. Click on attach and then Blaze DVD. Perfect. Let's start the application and then generate a PLF file. So double click again, we have a new PLF file, and then open this, open playlist, and then so we do see application has crashed. Okay, so EIP has been overwritten by 4 B's, 42, 42, 42, 42, and then ESP should start from D and not from C's. So let me go to the stack in ESP, and if you see we have D's at the ESP address. So we need to add 16 junk characters, which here in this case is 43, 43, 43, 43. So 4 bytes here, 4 bytes here, 4 byte here. So total of 16 bytes, and then we have EIP which has been overwritten by 42. So that's good. So we know 260 junk characters, then a memory address of ESP, then some junk characters, and then the payload. So that has to be the sequence. Now next is we need to identify bad characters, plus we need to identify a memory address. So let's first identify bad characters, and then we will see which memory address we can use to jump to the ESP. Again exit this. Let me close this, it is not required. Delete PLF file, and now we need a bad characters basically. So let me quickly get the list from the Google. Bad characters in buffer overflow. For example, go to this and we can get the bad characters from here. Okay, I've done a copy. Go to my Python script, click on edit, and then let's define and in fact do a copy. No plus is required here. Start the bracket, close it, and instead of D, now let me replace that with, and instead of that buffer name here, bad, and we have to send bad here. Perfect. So 260 A's, B's, C's, and then we have bad characters, and bad we have defined here. So good. Go to save, close this, launch application again, trial, closing this browser, and open debugger in the meanwhile. Attach the process. So this is a lengthy process. We need to do it again and again. Start the program again. Let's see if we have generated. No, we have not generated. So PLF should be generated in a second. I don't see a PLF has been generated now. Let me try again. Okay, because we have attached a process here. Click on exit. Something is wrong, we don't see. So let me pause the video for a second, and then let me troubleshoot this in offline mode. So there was some issue with the spacing in the file. Now I have the bad characters here defined, and I'm able to basically generate one PLF file. Let me start the process again. Then go to trial, start debugger, and then click on attach. Place DVD, attach, and start the process. Yes. So go to playlist, open PLF again. We could see crash. 42 42 42 has been written by EIP, and then let me see the bad characters in ESP. So go to dump. So we could see 1, 2, 3, 4, 5, in fact 9, B, C, and we don't have A here, we don't have E. So let me verify again. Uh, Open this, edit 1, 2, 3, 4, 5, 6. Uh, so A is not there again. Something is wrong with the bad characters. So let me add 1A here, x1A, and then slash, so that's the right one, 1A, sorry, not 1A, 0A. So 0A, 0B, C, then D is not there, so that's, let me quickly change this, not the right list of bad characters, strange. Okay, uh, let me go to some, one second. Okay, so now we have a right list of bad characters. uh, Let me close this file, go to open list, and then PLF, go to dump, and if you see, after 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 is not there. So that means 0 is one of the bad characters. So let me remove quickly that from the file and go to edit 0A. So 1A is also a bad character, so I'm removing that as well, because otherwise that will take time. So you guys need to see, you guys need to try basically what all characters are there. So now after 0A and 1A, I should be able to see complete information in a stack. So save this file. Let me delete this, generate a new one, go to Blaze DVD, and then launch debugger. Blaze. Start the process and import the file again in the playlist. Go to ESP, and now you could see from 1 till FF. So stack looks good now. No bad characters. So 0A and 1A and 00, these three are the bad characters. So we need to make sure while generating a payload, these three characters should not be there. Let me restart this application, and now I need basically a jump ESP address. Okay, let me see, go to trial, and in fact let me see the modules. So in last video we used user32.dll. So let's load that and try to search for jump ESP. So we have a jump ESP, but unfortunately we cannot use this jump ESP because this jump ESP memory address has 0A in it, and 0A, as per our analysis, is a bad character for this application. So our shell code will never execute because that 0A will not be accepted by the application. So we cannot use user32.dll here for this application. So let's try with, for example, ntdll. Let's go for commands and try to search. So we have a jump ESP here, and that looks okay because none of the bad characters is included in this memory location. So let me quickly note it. So go to, let's open a notepad basically and write this memory address 7C 941E and then ED. So we have a memory address now. Next step is generate a payload. I'm on the Kali MSF Phenome. So let me quickly first check my IP address. That is 192.168.1.9. MSF Phenome. Windows shell underscore reverse underscore TCP. Lhost would be my IP address 192.168.1.9 and L port I will choose as 443. Bad characters 00, 0A and 1A. These three were the bad characters. Encoder here will be Shikata underscore guy underscore nai, and then format should be C. So this should generate a payload which we can use in our exploit. So small change here, I have used a different slash. So now I should see a payload has been generated. Copy this and go to our Python script. Click on edit. And now we don't need bad characters, so remove them. Great. Define a new parameter shell and paste this, and paste that in bracket. So instead of bad characters we need shell. So let's revise this. 260 A's. Now instead of B we need to set a memory location which is in the reverse direction, ED1E, ED1E, and then ED1E 947C. 947C. So verify this again. ED1E 94 and 7C. Perfect. Close this. Then 16 knobs, because there is a difference between EIP and ESP, which is of 20 bytes. So 4 bytes is of EIP, and then we will send knobs which is 16, and then I need to specify knob basically for my shell to decode. So that is x90 and then multiply by, for example, 10 knobs, and then we have a shell here. Okay, so save this. Looks good now. Save this, close this. I don't need now debugger. Perfect. Open a handler on Kali to receive a connection on port 443. Launch the application. Go to trial. Let me remove old PLF. Generate a new one and import this. We have imported this PLF file, and now if you see, we can see a reverse connection from this machine to my Kali machine. And if you execute ipconfig, we are actually on this XP machine, which is 192.168.1.10. So that's all for this video. I hope you are enjoying this video series of buffer overflow exploits. So in next video, I will introduce concept of structure error handling, and then we will do a debugging of one such application. Thank you very much for watching this video.